Anytime you start talking about linear equations and graphs, you start with this, y equals mx plus b. Let's draw a line in the sand. And here's another line drawn in the sand. And if I wanted to compare these two lines drawn in the sand, how would I do it? Probably about 400 years ago, a guy named René Descartes, French, so there's an S on Descartes, but you don't pronounce it. So Descartes comes along and he says, tell you what we're going to do. Instead of drawing things in the sand, we're going to draw things on a grid. This is called the Cartesian coordinate system. It's a rectangular coordinate system. And so what Descartes did is he put an X here and a Y there just to label some axes. And then he put marks like a 1, a 2, a 3. Now with the Cartesian coordinate system, we can start identifying characteristics of lines. And let me get rid of these lines and let me draw a very nice line. And this nice line has a couple characteristics that almost every line has. Those characteristics are this point here and this point here. This point happens to be called the y-intercept because that's where the line goes through the y-axis, all right? And this is the x-intercept because that's where the line goes through the x-axis, right? So these lines, this line has a y-intercept and an x-intercept. And it turns out that the coordinates, I don't have to explain coordinates, right? Like you know coordinates, x and y ordered pairs. X is always the first one, y is the second one, in parentheses separated by a comma. This y-intercept has coordinates like maybe 0, 1.7. And the other one has an x-intercept. The x-intercept has coordinates maybe we'll say 2, 0. And so there's an important idea when you start putting coordinates onto the x-intercepts and the y-intercepts. The y-intercept always has a 0 for the x-coordinate. Y-intercept, 0 for x-coordinate. Likewise, the x-intercept always has a 0 for the y-coordinate. So now, if we were to draw two lines, we could compare these two lines. And we could say, well, if the two lines have the same x-intercept and they have the same y-intercept, they're the same line. Great. If they don't have the same, then they're not the same line. And so the green line and the blue line clearly are not the same line, not just because when you look at them, you're kind of like, well, that's not the same line. But when you put them on the Cartesian coordinate system, you can see that although they have the same y-intercept, they do not have the same x-intercept. So they're not the same line. So we can characterize every line by using x-intercepts and y-intercepts. But there's another characteristic that we like to define lines by. Slope. This is the Greek letter delta. And delta is a mathematical shorthand abbreviation for change in. So a weatherman may say delta T, which means the change in temperature. Like delta T was 10 degrees. That means the temperature went up 10 degrees. Delta T was -7. That means the temperature went down 7 degrees. So delta means change in. The variable that is used to define slope is m, and you pick that from the equation that we had up there, right? What else is slope equal to?
y2 minus y1 over x2 over minus.
Yep, that is the one, y2 minus y1 over x2 minus x1. My leading question I was going to ask to get you to that, what you just said, was how do I relate those x and y intercepts to slope? Right? So we just talked about a line. We talked about taking a line and giving it x and y intercepts with ordered pairs. How in the world do we relate those ordered pairs to the concept of slope? And you just answered that question. You take the y-coordinate of your second point, and which point is which is arbitrary, right? It doesn't matter which one's number 1 and which one's number 2. So in this case, if we take a look at the blue line that we had here, we're going to call this point number 1, we'll call this point number 2. So if we wanted to find the slope of the blue line, oh, that 1.7 is nasty. Can we change that? All right, so what is the slope of this blue line now that I've kind of given you some nicer numbers? So you say, okay, what is y2? So that means you look at the y-coordinate of point number 2. This is a 0 is your y-coordinate for the second point. The y-coordinate of the first point is a 3, so we say 0 minus 3. Divided by x2 is a 2, and x1 is a 0. And when you do this, you get -3 over 2. So that is our slope. The slope of the blue line, not only do we have the x-intercept, by plugging in a 0 for y, and the y-intercept by plugging in a 0 for x, we also have this idea called slope. It should be noted that slope is always, always, always a ratio. Slope is always composed of two parts. Change in y's over change in x's. Slope always has two components. And the way you relate these two components is this line going from whole number point to whole number point goes down 3 units and then goes to the right 2 units. So find the slope of the line that goes through these 2 points. So how about we call this, just to change things up, we'll call this point number 2. We'll call this point number 1. M equals y2 minus y1 over x2 minus x1. So we're going to say that the slope of this guy is 28 over 9, and you're done. That means if you had this graph and you knew 1 point, you would go up 28 units and you would go to the right 9, and that would be another point. And then you would go up 28, not drawn to scale, and then you would go to 9, and there would be another point. And you could connect all those points and you'd get a line. Next, graph this. This f of x, don't forget f of x just means y. So if we were to rewrite this, we'd say y equals 1/2 x minus 1. So that's our function. What I'm about to show you is what you do if all else fails. If you have no idea what the graph looks like at all, okay? So what you do is you make what's called an xy table. Usually they're done vertically this way, an x and a y. And the idea is that you pick an x coordinate, something along the x-axis, and yeah, you pick some easy numbers. The Fab 5 really are -2, -1, 0, 1, and 2. Those are the 5 numbers that you always want to pick. It gives you, they're simple numbers, they're small numbers. It gives you a mix of positive and negative numbers, and when you graph these numbers, it's going to fit in this nice window right here. You don't want to pick a number that's bigger than 5 because my graph is not bigger than 5, and I can't plot it, right? So sort of being aware of your environment. So these are nice numbers. So then what you do is you take each number and you do this. You take that number, you plug it into the equation. So 1/2 times -2 minus 1. And so 1/2 times -2 is -1. -1 minus 1 is a -2. And so now we have an ordered pair, the x coordinate, -2, and the calculated y coordinate, -2. And we would plot a point right there. Okay? And then you do this again. So you do this with the -1, and you plot a point. And then you do it with the 0, and you plot a point. Point, 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 point. Trust me, this is what these come out to be. This is one way to graph a line. Using the knowledge that you had from up above, where we said y equals mx plus b, you can say, well, I know the slope of this line is 1/2, which means up 1 to the right 2. And I know that the y-intercept is -1. So we'll plot the y-intercept. So you take this information and you plot the y-intercept. So you place a point at -1 on the y-axis, right? And now you sort of step off your slope. You go up 1 unit, you go to the right 2, and you plot a point. Up 1 unit, to the right 2, plot a point. Up 1 unit, to the right 2, plot a point. That's why it's important that we list our slope as 1/2 and not list it as 0.5. All right, what's your slope? 0.5. Okay, step that off. How do I don't know, I guess you go up 0.5 or 1 or something, right? The decimalization of 1/2 makes it difficult to handle the slope. So just leave it as 1/2. Determine the equation of a linear function, fancy words, that has a slope of -3/5. That's an important piece of information. So let's write it over here. M equals -3/5. And passes through the point 5, 5. So it goes through the point 5, 5. Write the equation in slope-intercept form. Plot the point first. 5, 5. 5, 5. There's the point. Okay, got the point. What's next? You're going to go down 3, 1, 2, 3, and to the right 5, 1, 2, 3, 4, 5, and you're going to plot a point there. Then you're going to go down 3, 1, 2, 3, and to the right 5, 1, 2, 3, 4, 5. Then, okay, so there's 3 points. Good, I'm solid there. What if I wanted to go in the other direction? The first one means go down 3 to the right 5. Then the second one means go up 3 to the left 5. So if I go up 3, 1, 2, 3, and now I go to the left, 1, 2, 3, 4, 5. Negative 5 means go to the left. Up 3 to the left, over here, and yeah, we're good. So we have a picture of the line, but in addition to the picture, we also need an equation. And the equation is y equals mx plus b. Do we know slope? Yeah, they gave us the slope. That's the negative 3/5. Do we know the y-intercept from our graph? What do you think it is? 0, 8. I like that you gave it as an ordered pair. Nice job. Are you sure? How do you know for sure from the graph? To really know, we're pretty sure the answer is 8. But maybe our graph is a little bit off. So what we want to do is we want to almost prove this, right? We want to do this algebraically. So there's no question. We have an idea that it should be 8, so we'll do our calculations. And if it comes out to be about 8, then great, things match up. The slope is negative 3/5. And look what we have here. We have an x-coordinate, and we also have a y-coordinate. So we're going to take that point that they give us, and we're going to plug them in for x and y. And so now we solve this. Does that match our graph? Yeah, it matches our graph. And we now know the y-intercept exactly. So let's put it all together. So the equation is going to be y equals the slope, which is negative 3/5, times x plus the y-intercept, which was 8. Y equals negative 3/5 x plus 8.